A building's envelope is what keeps the outdoors separate from the indoors. Natural Resources Canada and Carleton University are working together to make the indoors where we work and live more comfortable and energy efficient. Welcome to Caber Laboratories. Let's see if we can get someone to give us a tour.
My name's Alex Ferguson, and I'm a researcher here at Cabinet Energy Ottawa. Currently, we're standing at a brand new facility. We call this the Cabinet Energy Envelope Research Building, and it's a site that's designed to support envelope research construction and testing at our labs. One of the aspects that we're most excited about with this facility is it brings together Carleton University academic research onto our government facilities here. Now, my colleagues and I have a lot of experience working with home builders, with architects and engineers. We do a lot of work with manufacturers, and we do a lot of work to take those insights and improvements into the building code. What Carleton brings to this site is more than just excellence in building science. They also bring a lot of new ideas. They have graduate students who are bringing with them a wealth of creativity. This facility will draw those two communities together to accelerate innovations in our building sector.
My name is Cynthia Cruickshank. I'm a professor at Carleton University, and I am the director and lead researcher here at Caber. Caber is a new research facility focused on building retrofits and also new construction. So we're looking at how to build better buildings, more healthy buildings, buildings that are more resilient for future climate change. The majority of our building stock consists of buildings that are 60 to 70 years old. So we have to ask ourselves a question: do we demolish and rebuild, or do we renovate? Do we retrofit the building? What we're doing here at Caber is that we're looking at new ways of retrofitting those buildings using new materials, better insulating materials. And we're looking at new techniques that are affordable and sustainable. There are three main parts to Caber. The first part is our large two-story guarded hotbox. Now, this guarded hotbox allows us to study how much heat, air, and moisture travel through that building envelope. The second one is our pressurized spray rack. Our pressurized spray rack looks at how we can saturate different wall samples and look at points of failure, look at air sealing as well. And then the third part is our Insitu samples. So Insitu samples allow us to do long-term study of how, again, these building envelopes perform for different outdoor weather conditions.
My name is Christopher Baldwin. Today I'm going to talk to you about our guarded hotbox, which is our largest piece of equipment situated behind me. We use this to test heat, air, and moisture transfer that occurs within the building envelope. And to do this, we have an environmental chamber that we use to represent the outdoor conditions. This chamber we can bring down to minus 35 degrees Celsius, up to 55 degrees Celsius, and represent any exterior condition or weather that you would see within the Canadian environment. So this is the sample that we're testing. In this case, it's insulating foam that we're testing currently. And you'll notice that all these wires that we have installed are actually thermocouples. And this is what we use to get the actual temperatures and the performance metrics that we're looking for within the sample. To my left here is our interior conditions represented through our guard box, which is the outside box to my left, and our metering box, which is the inside box. One of the questions I quite often get is, why do we have a box within a box? That's to get better measurements and more accurate measurements by protecting the conditions that this inner box where we actually take our measurements occur. We keep this box between 15 and 35 degrees Celsius, and we can also control the humidity as well as the airflow within the space. To do the actual test, this box to my left moves along these rails below me and goes right up against our sample. So the sample becomes sandwiched between the two boxes, and through this we can measure the heat, air, and moisture transfer that's occurring from our environmental chamber through our sample and into our interior conditions. To accurately measure the performance of samples within this facility, we've installed approximately 1,800 channels of data acquisition that are able to measure things like temperature, humidity, pressure, heat flux, and any other values we might be interested in within the building environment or the building envelope. This is one example of a board we've created that allows us to quickly connect and disconnect samples, instruments that are within different samples to do things like temperature in this case. So each of these blue lines or blue connectors represents one temperature sensor that we'll be monitoring. And this is one of about 6 or 8 of these boards that are situated throughout the facility. In total, we've installed over 200,000 feet of thermocouple wire that allows us to take approximately 1,000 different temperature measurements throughout our facility.
This is inside the climate box, which is a key component of our guarded hotbox experiment. This is where we control the outdoor conditions, if you will. We can drop this box from anywhere to -35 or heat it up to +55. So we're inside the climate box right now. This is, again, where we want to control very accurately our outdoor environment. Big piece of equipment right here, you'll notice this fan coil unit and another similar one right above it. These are essentially what blows our cold air into here to really cool this box down. On top of that, we have our solar lamp rack that you can see all the rows of solar lamps. So this is what we use to simulate solar exposure onto a wall sample. I believe there's 96 lamps. So when you're thinking of controlling the environmental conditions, we have temperature, humidity, and pressurization. So we also have 2 humidifier units in here. And also these air handling units have heaters with them, so that's what we use to heat up the space. Right now you can see kind of some different tubes going here. This is what we're using to measure the air velocity. That would be simulating wind, or for example, against your surface. You'll notice across the top we have 6 large fans, and this is what we use to pull air up along our sample surface. So essentially the air flows in underneath here through all these holes and goes up along your sample and out along the top.
So the other major piece of equipment within our lab is the pressurized spray rack, which we're currently standing in. This piece of apparatus is used to test the air tightness and water tightness of building envelope assemblies under different rain events and pressures. We have 96 nozzles that can be seen here that create a cone of water that represents the rain hitting our surface, in this case vinyl siding that we currently have installed. Through this piece of equipment, we can test things like window seals, how well different claddings work, as well as how airtight a building is for both resilience and energy performance. Through these 96 nozzles, we can get about 150 liters per minute of total rainfall, which is the equivalent of about 25 millimeters per hour hitting our surfaces. So this would represent a very heavy rainfall. Typically you see rainfalls of the sort of couple millimeters per hour range, and a heavy rainfall would be in the sort of 10 to 20 millimeter per hour range.
So at Caber, we have 6 in situ wall openings. So we have 6 sections of the base building that can be removed and replaced by wall samples that we want to test. 2 of the in situ wall openings that are located on the south facade have been removed and replaced with these 2 chambers that you see behind me. Now, if you follow me, I'll show you a little peek inside one of the chambers. Okay, so welcome to one of our chambers. We have the south wall here, which has a window in it, and this south wall is exposed to the elements outside. And then inside, with the door closed, we monitor the temperature conditions, the solar energy that's coming into the space, and also the energy that's moving throughout the space. You can see all of these wires hanging down that are brown. Each one of these wires is a thermocouple, which measures the temperature of different parts of the space. Some of our thermocouples are taped to the walls, some of them are taped to the floors, and some of them are measuring the air temperature within the space. We also have a pyranometer, which is attached to this yellow wire. This pyranometer is measuring the amount of solar energy that's going onto the floor. And then these white wires are heat flux sensors, which measure the amount of heat going through the wall. We also have this heating and cooling coil. This is how we maintain the temperature set point within the chamber. If the temperature of the space is less than the temperature set point, then warm water will flow through this cooling coil, and we have a fan blowing over the coil to send that energy to transfer it to the air within the space. The purpose of these chambers is to test some sort of new material or new control strategy or occupant comfort. So these chambers are both built out of typical wall constructions and typical materials. One chamber is going to serve as a reference case, and the other chamber is going to have some sort of new idea that we want to test and compare to a base case. Some examples of this include we could add new material into the drywall that is better able to store solar energy. This makes the space temperature more uniform and also decreases space heating and cooling loads throughout the year.
Canada's building stock is aging. Many of our homes and buildings are going to require renewal as we move into the later part of this century. Traditional renovation and retrofit techniques tend to be quite expensive and disruptive and difficult to implement on our homes and buildings. This facility offers new opportunities for us to prototype, test, and validate solutions for factory-built wall systems that make it less expensive and less disruptive and less timely to improve our buildings, make them more energy efficient, more comfortable, and get them ready for the next century.
If you like this video, let us know with a thumbs up. Click on the logo below to subscribe to the Simply Science channel and click the bell icon to be notified when we upload new videos.